Hey everybody, we're still in chapter 5. We're getting halfway through it. Today we're in section 5.4. So when we last left off, we learned that there are some identities that we're going to use that don't just relate to one angle, but they relate to two, alpha and beta. Or as your textbook says, A and B, capital A, capital B. And we learned that these identities were sum and difference identities. The two angles were connected by addition or subtraction. And in 5.3, we did these identities related to the trig function cosine. So in 5.4, we're going to do the same identities, sum and difference identities of two angles, alpha and beta. But instead of using cosine today, we're going to be using sine and tangent. Now, like we said, these identities do not need to be memorized. They're a little bit lengthy, and really, in all honesty, they're not as important as they were back in the 80s and before that, because now we have the use of a calculator. But you do need to understand the importance of why they needed to be in existence and how to work with them. So you do not need to memorize these identities. They will be given to you on your chapter test, but you do need to know how to work with them. So again, what was the purpose of having a sum and difference identity of two angles? Well, it went back in the early days, when I was in school, you had to know how to look up trig function values of any size angle. And remember, the only angles we can look up without a calculator are our quadrantals off the unit circle, our 30, our 45, and our 60, because we know those side relationships. So when I was in school, if I asked you to look up the sine of 75 degrees or the tangent of 75 degrees, you couldn't go to the unit circle. 75 degrees is not a quadrantal angle. You couldn't go to the triangles because the triangles didn't have a 75-degree angle on them. And we didn't have access to calculators. So how did we look up the sine of 75 degrees? Well, what we did is we used our brain and thought, what two angles that we can look up would either add or subtract to make 75 degrees? So we'd go through the list of our quadrantals, 0, 90, 180, 270, 360. We'd go through our 30, 45, and 60 and say, is there a way we could take two of those angles and either add them or subtract them to get 75? And sure enough, if you think long about that for a minute, it makes sense. You can rewrite 75 degrees as 30 degrees plus 45 degrees. So what you're doing is you're changing one angle, 75, into two angles, 30 and 45. So that's where the alpha and beta come from. And if I was adding and we were doing sine, I would use this identity. And if I was adding and doing tangent, I'd use this identity. Now, I'm not going to spend time developing where these identities came from. It's too lengthy for the video. They are in your textbook if you want to look through your textbook and see those proofs to develop them. What you need to learn and understand how to do is figure out which of these identities we're going to use and use it. So again, the first most practical way to use these identities is to look up a trig function angle, its answer, if it's not quadrantal and not on the right triangles. So let's get to our notes to example 1b. If I want to look up the tangent of negative 105 degrees, I know that's not a quadrantal angle, and I know it's not 30, 45, or 60. So what I got to do is I got to break this up into not one angle, but two. I need an alpha and a beta. And the hard part is the thinking part. Can I think of two angles that will either add to negative 105 degrees or would subtract to negative 105 degrees that I can look up? So let's think a minute. What angles could we use? Remember, we have 0, 90, 180, 270, 360, 30, 45, and 60. If you think about it, there are two angles that we can look up that we can add to make negative 105. And the two angles I'm thinking of are 45 and 60. 45 plus 60 would make 105 degrees. So if I want to add to negative 105, my angles are going to be negative 45 degrees plus negative 60 degrees. And what I've just done is I've changed this one angle into two. So now I have an alpha and a beta. Because I'm looking up the tangent and I'm adding these angles together, I would use this identity. So I'm looking at my list. I got tangent. I have two identities picked from. In between my two angles, I have addition. This is my identity, so I'm going to write it down. This is going to equal tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Now, all we got to do is substitute. Big A and big B stand for the angle measurements. Well, we know the actual angle measurements. You told me you're going to let angle A be negative 45 and angle B be negative 60. So I'm going to rewrite this. So this is going to become the tangent of negative 45 degrees. I'm going to put that in parentheses to show it's an angle, plus the tangent of negative 60 degrees. I want to show that that's the angle. I do not want it to look like tangent minus 60 because that doesn't make sense. Then I'm going to substitute into my denominator 1 minus tangent negative 45 degrees times the tangent negative 60 degrees. So far, so good? Great. Now, this is what I would do. I would then say, okay, I need to look up these angles. But negative 45 and negative 60 are in what quadrant? Correct. They're in quadrant 4. So if we go back to chapter 1 and we draw an angle in standard position, we know the initial ray is on the positive x-axis. We know because this angle is negative that our terminal ray would rotate clockwise. So we know that from here to here is negative 45 degrees. We also know from this angle we can drop a perpendicular and make a right triangle. The problem with working with a right triangle is the angle inside has to be acute. The word acute means between 0 and 90 degrees. So you can't have a negative angle in your triangle. So we got to think. If we can't leave this labeled as negative 45 degrees, then what is it? Well, it goes back to the whole concepts from chapter 1. If I go back 45, that would be like going forwards how many degrees? Going back 45 is like going forward 315 degrees. Those are co-terminal angles. Their terminal ray lands in the same position. The problem with the 315 degrees is it's not inside the right triangle. So we talked about this. We all agree negative 45 degrees is an angle in quadrant 4 because that's where the terminal ray lands. We all agree 315 degrees is an angle drawn to quadrant 4 because that's where the terminal ray lands. But to get the angle inside the triangle from chapter 1, that's where our reference angle rules came from. So if you're in quadrant 4, the reference angle rule was 360 minus theta. Your angle is 315. And that gives you 45. So you know when you draw the right triangle, this angle inside can't be negative 45, it's positive 45. And we've already discussed this. We've already said once before in our previous lectures, when you have an angle in quadrant 4, the reference angle that's inside the triangle is just this angle being positive. So I don't have to go through all this work to figure out what the reference angle is for negative 60 degrees. If I'm looking up the tangent of negative 60 degrees, I'm really looking up the tangent of positive 60 degrees. But let's go back to this negative 45. So looking up the tangent value in negative 45 degrees without a calculator would be like looking up the tangent of 45. And we know the sides of the 45, 45, 90 right triangle. They're 1, 1, square root of 2. But because we're in quadrant 4, the y value is going down, so the y value is negative. To look up tangent, we go back to our definitions. Tangent is y over x or opposite over adjacent. Put your finger on the acute angle. Y over x. That would be negative 1 over 1, which is negative 1. Or if you do it opposite over adjacent, you still get negative 1. Okay? I want to look at the tangent in negative 60 degrees. Well, I can't use that triangle. That's the triangle sides for 45. So again, if I draw me a right triangle, and I draw it in quadrant 4, because that's where negative 60 degrees is located, I can't mark this angle negative 60, because if I draw a right triangle, I need the acute angle. If that's a negative 60 degrees, the acute angle is really the opposite, the positive of that, which is positive 60. Now that I know that's a 60-degree triangle, I know the side opposite is square root of 3. I know the hypotenuse is 2, the other side is 1. Because we're in quadrant 4, the y value is going down, so the y value should be negative. So I found the tangent in negative 45 degrees. It was negative 1. I brought down the plus. The tangent in negative 60, here's my finger on the 60. Again, y over x, or opposite over adjacent. Negative square root of 3 over 1 is negative square root of 3. Everybody okay with that? Now I'm going to fill in the denominator. Well, there's no work. I already know these values. I got a 1, a minus. What do we say the square root of negative 45, tangent in negative 45 is? We said that was negative 1. Then we have the tangent in negative 60. We said that was negative square root of 3. They're side by side, so they're connected by multiplication. That's the trig part. Is everybody okay so far? Now, here comes the hard part. Is this acceptable? Remember, if you have a fraction bar, the answer is a fraction. Is this an acceptable fraction? You better say no. There's no way that's an acceptable fraction. We discussed this. The denominator of a fraction must be a positive whole number. So, in the numerator, there's nothing to do. I cannot add a negative 1 to a negative square root of 3. They're not alike. But you know in math, in front of every number should only be one symbol. So what kind of 1 is this? It's negative. But we do not write plus a negative square root of 3. If it's a positive and a negative, it makes a negative square root of 3. So there's my numerator. My denominator, I can't subtract until I multiply here. So I'm going to keep the 1. I'm going to keep the minus. What do we know about a negative times a negative, people? It's a positive. What's 1 times square root of 3? That's square root of 3. Now, do we really need to write plus square root of 3? No, because a minus plus square root of 3 is just a negative square root of 3. Is everybody with me? Now, look closely at that and think, is that acceptable? Okay, you better be telling me no, because we still do not have a whole number down here. Here's the biggest mistake you all make. You all jump the gun. You know the fraction bar means division, and you see a square root of 3 over a square root of 3, and you want to divide it out. Well, guys, you can't do that. And it has nothing to do with algebra. It has to do with arithmetic. You can only do division when you are connected by multiplication. We've been through this. Again, let's recall facts. If I write in good old arithmetic, 2 plus 3 divided by 3. Can you do this? Oh, let me divide by 3. That'll leave me 2 plus 1. Absolutely not. We all know if we have the fraction 2 plus 3 divided by 3, we add first. That'll give us 5. And 5 over 3 is 1 2/3. If you divide first, you're going to get 2 plus 1, which is 3, which is not the same value. So that is why it's important you understand rules. You can only do division when you are connected by multiplication. This is not multiplication. Listen to how I read it. Negative 1 minus square root of 3. I said minus, not multiplication. This is 1 minus square root of 3. That's not multiplication. So you can't do division. So the question is, I just leave it. Absolutely not. Can't leave it. The denominator's got to be a positive whole number. So now we got to make an equivalent fraction, which we've been doing all semester. How do we change 1 minus a square root of 3 into a whole number? Well, we do multiplication. So let's think. We've been doing this all semester. Every time we look up a value like the sine of 45 degrees and we get 1 over square root of 2, don't we rationalize by multiplying by square root of 2 over square root of 2 and getting square root of 2 over 2? So you've been rationalizing all semester. You know you can't leave a square root of 2 in the denominator. You know you can't leave a square root of 3 in the denominator. You can't leave a square root of 5 in the denominator. But those were monomials. They were only one term. So when you have one term, you multiply it by itself. Here's the problem. There's not one term down here. There are 2. So to get rid of 1 minus square root of 3 and make it a whole number, you don't multiply by 1 minus square root of 3. You multiply by its conjugate. Algebra word, The conjugate means to change the middle symbol. So the conjugate of 1 minus square root of 3 is 1 plus square root of 3. And if you multiply the denominator of the fraction by the conjugate, you have to multiply the numerator of the fraction by the conjugate. Now we're going to do that up here. So we know multiplying fractions is no problem. Top times top, bottom times bottom. To multiply two terms, a binomial, times two terms, a binomial, is the FOIL method. So here we go. We're going to go first. We're going to go slow. First, negative 1 times 1. That's negative 1. Outers, negative 1 times a positive square root of 3. A negative times a positive is a negative. 1 times square root of 3 is square root of 3. Inners, negative square root of 3 times 1. A negative times a positive is a negative. Square root of 3 times 1 is square root of 3. Last, negative square root of 3 times positive square root of 3. A negative times a positive is a negative. Square root of 3 times square root of 3 all semester has been square root of 9, but the square root of 9 is 3. Now we got to multiply the denominator. Again, it's a binomial times a binomial, which is FOIL. However, you did learn a trick. Back in algebra, you should have learned when you multiply conjugates, you don't have to do FOIL because the outers and the inners are going to be opposites and cancel out. So watch, when I do FOIL down here, first, what's 1 times 1? 1. Outers, what's 1 times a positive square root of 3? Well, that would be positive square root of 3. If I do the inners, what is negative square root of 3 times 1? Well, that would be negative square root of 3. And when you take a positive square root of 3 and add it to a negative square root of 3, that makes 0. It cancels. So anytime you multiply two binomials that are conjugates, you are guaranteed that outers and inners will cancel. So that's why when we multiply conjugates, we just do the first and the last. So again, the first is 1 times 1, which is 1. And the last is negative square root of 3 times positive square root of 3. Well, a negative times a positive is a negative. Square root of 3 times square root of 3 is square root of 9, which is just 3. That's still not acceptable. Let's collect like terms in the numerator. So in the numerator, you have a negative 1 and a negative 3. That will add to negative 4. You have a negative 1 square root of 3 and a negative 1 square root of 3. That would add to negative 2 square roots of 3. And in the denominator, 1 minus 3 is negative 2. All right, we're getting close. This is still not acceptable because the denominator has got to be a positive whole number. So how do you get the negative out of there? You float it to the top. But there are two terms at the top, so you're dividing them both. So everybody look, that's a negative 4, and you're dividing it by a negative 2. What is negative 4 divided by negative 2? That's correct, it's positive 2. That's a negative 2 square roots of 3 divided by negative 2. Well, a negative divided by a negative is a positive. Now, if I write 2 square roots of 3 divided by 2, we can divide that because we are connected now by multiplication. That's 2 square roots of 3. That's connected by multiplication. So the 2's would cancel and leave you with square root of 3. And this right here, sweethearts, is the exact value of the tangent at negative 105 degrees. Now, what's great about you guys versus me is when I was in school, I had no idea if this was right or wrong. I just had to trust in my gut that I did the work correctly. You guys can now check yourself by using your calculator. So that's what's great about your calculator. If you go in and type in the tangent negative 105 degrees, first of all, what mode do you have to be in? That's right, be in degree mode. Hit the button tan and type negative, baby negative 105 and close it. And if you do that, the calculator is going to spit out a decimal. And the decimal they spit out is 3.732050808 ... Now I know what you're saying, but Miss Black, we didn't get a decimal. We got this expression. Type in your calculator 2 plus square root of 3. So type 2 plus second square root, put the 3 in, hit equals. And I guarantee you're going to get out the same decimal value, which proves to you did it correctly. Okay? Is everybody okay with that? So the most important thing we learned is the purpose of having these identities was to find the trig function value of an angle that we couldn't normally look up on our own. All right, I'm going to erase example B. Let's go to example C in the notes. Okay. Example C in the notes says again, evaluate, give me the value. Now, if we look closely at this expression, our problem is, what are all our angles in? Radians. Okay, that's okay. We may not know what angle is 2 pi over 9 or 5 pi over 18. What I want you to notice, how many different angles do you have? Good, you have 2. 2 pi over 9 is representing one angle, so I'm going to call that alpha. 5 pi over 18 is representing a different angle, we're going to call that beta. So if you look closely, we have sine alpha cosine beta plus cosine alpha sine beta. That is one of these identities. Now all we got to do is match it up. Well, it doesn't have the word tangent in it, so that knocks out the tangent identities. So is that up there, is this expression the sum of the sine or the difference of the sine? Well, it has a plus, and it matches to here, which has a plus. So we do have sine alpha cosine beta plus cosine alpha sine beta. So this time, we have the right side of the identity, and we know it equals this, the left side. So this expression all equals the sine of alpha plus beta. Y'all with me? I'm just matching them up. Now I'm going to fill it in. According to you guys, alpha is the angle 2 pi over 9. Beta is the angle 5 pi over 18. According to operations, we do it inside parentheses first. I got to add these two angles in radian measure, so I need a common denominator, which would be 18. So I'd multiply 9 by 18. I multiply by 2. So 2 times 2 pi is 4 pi. This denominator is already 18, so I'm going to leave it alone. Now I can add 4 pi over 18 plus 5 pi over 18 would make 9 pi over 18. But what do we know that reduces to? That's right. 9 over 18 is 1/2. So the 9 would go away, and the 18 would become a 2. Now, because we've done graphing, we know this by heart. Pi over 2 is how many degrees? That's right. We're really looking up the sine of 90 degrees. And we know where to get that from, our buddy, the unit circle. 0, 90, 180, 270, 360. We're looking up the sine of 90, so we need the coordinate at 90, which is 0, 1. Sine is always y. Your y value is 1. Now, if you want to go prove it to yourself, you're right, go for it. But in order to type this original expression in your calculator, what mode would you have to be in? Correct, you'd have to be in radian mode. So you'd have to change from degrees to radians. So if you put yourself in radian mode and then you type sine 2 pi over 9, cosine 5 pi 18, plus cosine 2 pi 9, sine 5 pi 18, and hit equals, it should spit out a 1. Okay? Everybody's good? All righty. We're going to do one more example in notes, and this is example 3. All right? All right. It says, use the given information to find the following. It has 3 parts. They want us to find the sine of s plus t. They want us to find the tangent of s plus t. And they want us to find the quadrant s plus t is in, what quadrant it's in. All right. Now, instead of using alpha and beta, A and B, they're using S and T again. I particularly don't like that. If you want to change it to alpha and beta, be my guest. All right, let's look at what they give us, though. This time they give us this information. They say the cosine of S is 3/5, and the sine of T is 5/13. So here's the problem. We want to find the value, the answer to what sine s plus t is. So we have an alpha and a beta. We have 2 angles we're adding. So we know the sine of s plus t would be this first identity. We got the right side, Instead of using alpha plus beta, they're using s plus t. So they want us to find the left. They're giving us the left side. I apologize. They're giving us the left side, sine s plus t. They want us to find the right side. So I'm going to write it down. So this is going to be sine alpha cosine beta plus cosine alpha sine beta. But instead of using a's and b's, what are they using, guys? That's right. They're using s's and t's. So I'm going to rewrite this with the s's and t's. So the sine of s plus t equals sine s cosine t plus cosine s sine t. Wherever there was a, I put angle s, because that's what's happening here. S is in the a. And wherever I have t, I put for b. Now, the problem is I don't know actually what angle measurement s and t is. Nowhere given does it say angle s is 45 degrees. Angle t is 30 degrees. So you're going to say, well, I can't do this. I can't look it up without the angle. Yes, you can. Trig is a relationship between an acute angle and two sides, which means without knowing the angle, you could still draw a picture of a right triangle and find the value. So that's what we're going to do. We're going to resort back to chapter 1. From chapter 1, if we were giving cosine s is 3/5, we know we have our definition of cosine. We have to draw a right triangle. Okay? So we draw a right triangle. Here's our angle s. Cosine is x over r. And we'd have to find our missing side. Now, we could do Pythagorean theorem. X squared plus y squared equals r squared. Or if you remember, this is a 3 blank 5. It's a 3, 4, 5. Now, what quadrant am I in? Well, it says in the directions, S and T, angle S and angle T are in quadrant 1. And if we're in quadrant 1, we know all our numbers are going to be positive. Now, the problem is we're not just given acute angle S. We're also given acute angle T. So that's a totally different right triangle. So I'll get out a different color. We're given in the directions. All this information is in quadrant 1. So that's why I'm drawing it this direction. There's angle T. The definition of sine was y over r. Here's our y value. Here's our r value. We would do Pythagorean theorem, x squared plus y squared equals r squared. Or if you remember, this is one of your triplets. It's a 5, 12, 13. Because we're given it's in quadrant 1, we know all our numbers are positive. Now, guys, without even knowing the angle measurements, I still don't know how big angle S and angle T is. That's okay. I can look up these values. I can substitute now because, look, I could look up the sine of S because I'll go to angle S and sine is opposite hypotenuse. I get 4/5. I can look up cosine T. Go to angle T. Cosine is adjacent hypotenuse 12 over 13. Or x over r. I can use either definition. These two trig functions are side by side, so that means these fractions are connected by multiplication. Plus cosine s. Here's s. Cosine x over r. Sine t. Here's t. Sine y over r. So without knowing what angle S and T are, you still can look up the relationship of the two sides to that acute angle using your right triangle. Now it becomes arithmetic. We have fractions connected by multiplication, so we multiply. Top times top, 48. Bottom times bottom, 65. Top times top, 15. Bottom times bottom, 65. Says add. We got a common denominator. This makes 63 over 65. So we answered the first question. The sine of angle S with the sine of angle T added is 63 over 65. So without actually knowing how many degrees angle S is and how many degrees angle T is, if we added those two angles together and took their sine, that's the answer they would get. Okay? Now we're going to do it again for tangent, S plus T. So if we're looking up tangent of S plus T, we're not using this identity. We're going to use the same given information, but a different identity. Because now we're looking up what trig function? Tangent. I want S plus T, so I'm doing a sum of tangent of two angles, and here's my identity. They are giving us the left side. Instead of using A and B, they're using S and T. We're going to give them out the right side. So we know the tangent of S plus T would equal the tangent, instead of using A, we're using S, plus the tangent, instead of using B, we're using T. 1 minus tangent S, tangent T. Again, even though we don't know the actual angles, we have right triangles to look at. So we know how to look at the tangent of S. We go to angle S, and tangent is y over x, or I don't care if you say opposite over adjacent. That would give us 4/3, plus the tangent of T. Go to angle T, y over x, 5/12, over 1 minus tangent x, S was 4/3, tangent T was 5/12. Again, all these numbers are positive because it's in direction. Angle S and angle T are in quadrant 1. All right, so far so good. Now all we're going to do is do our arithmetic. In our numerator, it says to add. Well, to add fractions, we need a common denominator. What's the common denominator? 3 and 12? That's right, it's 36. I'm going to change both of these to 36s. 3 becomes 36 by multiplying by 12. So 4 times 12 makes our numerator 48. 12 becomes 36 by multiplying by 3. So 5 times 3 is 15. Now I can add my numerator, and I'll get 63 over 36. So that's what I have in the numerator, a fraction. Now my denominator. I can't subtract yet because I got to multiply. So this becomes 1 minus, we're going to multiply, 4 times 5 is 20, 3 times 12 is 36. To subtract, I need a common denominator. The common denominator of 1 and 36 is 36. So this really becomes 36 over 36, which is 1, minus 20 over 36. And 36 minus 20 is 16 over 36. Okay? Now, can't leave this because we're dividing. There's no such thing as dividing fractions. You multiply by the reciprocal. So this becomes 63 over 36 times 36 over 16. The 36 will divide out, and you'll be left with 63 over 16. And that's in lowest terms because they have no common factors. So again, without actually knowing how many degrees angle S is, and without knowing how many degrees angle T is, if you added those angles up, made a new angle, and took the tangent, that would be your answer. Okay? Now, here comes the thinking question. They want to know what quadrant angle S plus T is in. Now, let's think about this a minute. Angle S was in what quadrant? That's right. They told us in the directions. Angle S is in quadrant 1. So if angle S is in quadrant 1, it can't be any smaller than 0 degrees, and it can't be any larger than 90 degrees. Make sense? And if angle T, they said in the beginning, was in quadrant 1, again, it can only be as small as 0 degrees and as large as 90 degrees. So if we took these two angles and added them up, the smallest they could still be was 0 degrees, right? If I added 0 and 0, it'd still be 0. The largest they could be is if I added 90 and 90, which is 180. So if I take angle S and angle T and add them up, I can get an angle measurement anywhere between 0 and 180. Do you all agree with that? Think about it. If angle S is 55 degrees and angle T is 40 degrees, that would add to 95 degrees. That could put us in quadrant 2. But if angle S is 10 degrees and angle T is 12 degrees, that only gives us 22 degrees. It would still keep us in quadrant 1. So that's what you're saying. If both of these angles, S and T, were told are in quadrant 1, they're as small as 0 and as large as 90. Well, if I'm adding them up, my sum could be as small as 0, because 0 plus 0 is 0, or my sum could be as large as 180, because 90 and 90 is 180. So that means angle S plus angle T could either be in quadrant 1 or quadrant 2, because to go from 0 to 180 degrees is covering both those quadrants. So how do you decide what quadrant angle S and angle T are in if you don't actually know them? Well, look at what you found out. You found out when you added angle S and T and you found their sign, their answer was positive. And you found when you added angle S and T and did the tangent's positive. What quadrant is both sine and tangent positive in? Quadrant 1 or quadrant 2? That's right, quadrant 1. So that's how you decide where those two angles, their sum would be represented, because you have to think about it that way. It's going back to those sine values. Okay, we still have 2 more big sets of identities to go. So I will see you in the next section. Practice this. It just takes practice.